There's nothing better than a good science fiction movie. The kind where the star is a giant-sized creature that looms over cities, wreaking havoc with a single step. Getting caught up in the adventure of watching this monster destroy London almost makes us believe that it exists as portrayed here. But it doesn't exist, and the truth of the matter is, it can't. You see, the people who dream up these sci-fi monsters sometimes don't know very much about math or biology. With a few simple principles of geometry, we can prove that giant-sized dinosaurs, lizards, or apes, as seen in the movies, are a mathematical impossibility. It all has to do with something called the problem of scale. But before we set Hollywood straight about the mathematics of monsters, we need to understand a basic but powerful idea of geometry called similarity. You already have a sense of what it means for two objects to be similar. To illustrate the concept, I'll hold up two objects, and you decide whether or not they're similar in the mathematical sense. Let's start with these. Definitely not similar, right? Okay, how about these? Well, they're pretty close to being similar, but they aren't really. Here's where it gets sticky. What do we say about these? Well, they're similar in size and shape, but they're made out of different materials. So you wouldn't want to say they're similar, unless, of course, you were a mathematician. By geometric standards, two objects are similar as long as they're the same shape. Let's try a slightly trickier comparison. These are the same shape, their angles are the same, and the proportion of their heights to their lengths are the same. But they're a different size. Are they similar? Yes, because geometrically speaking, size doesn't matter. Similarity is based solely on shape and proportion. Geometric similarity gives us the groundwork for tackling the problem of scale. I'm going to illustrate the problem of scale with cubes, which are regularly shaped and easy to work with. I'll get back to monsters in a bit. When this cube is magnified 3 times, it becomes 3 times as long, 3 times as high, and 3 times as deep as the original. The number of times we enlarge an object is called the scaling factor, which in this case is 3. But what happens to area? Look at the front face. It's 9 times as large as the original. So when we scale up this cube 3 times, the area of each face goes up by the square of 3, or 9. Since all 6 faces of this cube have the same relationship to all 6 faces of this one, the total surface area of the enlarged cube must also go up 9 times. In general, the area of a scaled-up object goes up with the square of the scaling factor. Now that we've taken care of area, let's move on to volume. How does the volume of the large cube compare to the volume of the small one? Let's count the number of small cubes I used to make up the big cube. There are 3 layers with 9 in each layer, for a total of 27. That means the volume of this cube is 27 times greater than the volume of this cube. The volume increased not by 3 times, but 3 times 3 times 3 times, or 27. In general, the volume of a scaled-up object goes up with the cube of the scaling factor. There's a general mathematical expression for what we've just learned about area and volume. Let's call m the scaling factor. The area of the scaled-up object is m times m, or m squared, times the area of the original object. And the volume of the scaled-up object is m times m times m, or m cubed, times the volume of the original. There's another factor that must be considered when an object is scaled up. Its weight. Say our cube were made out of steel, not wood, and its dimensions were 1 foot by 1 foot by 1 foot. Such a steel cube weighs about 492 pounds. The bottom face of the cube supports the weight of the entire cube. The pressure exerted on the bottom face is equal to the weight of the cube divided by the area of the bottom face. In this case, the pressure exerted is 492 pounds per square foot. When we double the size of the cube, the enlarged cube is now 2 feet on a side. The area of the bottom face is now 4 square feet. And as we've just learned, the volume of the cube goes up by the cube of the scaling factor, 2 cubed, or 8. Since weight is proportional to volume, the scaled-up cube is 8 times heavier than the original cube. When we divide the weight by the surface area of the bottom face of the cube, we see that the pressure being exerted on the bottom face is 984 pounds per square foot, twice the pressure on each square foot in the original cube. What happens if we keep increasing the weight by a factor m cubed and the surface area by m squared? At some point, the pressure due to the weight of the cube will exceed the steel's ability to withstand that pressure, and the steel will collapse under its own weight. That point for steel is reached when the cube is slightly over 4 miles on a side. We call a material's ability to withstand pressure its tensile strength. So when a steel cube is over 4 miles on a side, the pressure exerted due to the cube's own weight exceeds the tensile strength of steel, and the cube collapses. Let's go back to our original cube. It's supporting all of its weight on one face. In the scaled up version, the one that's 3 times larger, each small cube of the bottom layer is supporting its own weight, plus the weight of the 2 other cubes piled on top of it. But say we design our scaled up cube a little differently, and let's concentrate on only the front face, or these 9 smaller cubes. We'll take 3 of the cubes in the top row and move them to the bottom, and then we'll cut the remaining cubes in half and put a half piece each over the cubes on the bottom row. We still have the same volume and weight that we started with, but now there's less pressure on the bottom face. Each cube in the lowest row now supports only its weight and a half cube's weight. Of course, the scaled up object is not similar to the one we started with. By changing the proportions of the scaled up object, we were able to compensate for the scale problem. We can figure out how high the tallest mountains can be. Given the tensile strength of granite, which is about half that of steel, it works out that the tallest mountain can only be about 7 miles high. That's not too far from the actual tallest mountain, Mount Everest, which is a little shorter than 6 miles high. And the tallest trees can't be much higher than 330 feet. So in nature, the concept of scale puts a definite limit on the size of things. One way architects get around the problem of scale when designing structures is to use stronger materials, compensating for the fact that volume increases faster than area. Since urban architects are constrained by the scarcity and high cost of property, they need to design up instead of out. That's why skyscrapers are built with steel and reinforced concrete instead of wood. You see, if you want to scale up an object, you might have to change its design by either changing its proportions or the materials it's made of. So if a big-time Hollywood producer asked me for my professional mathematical opinion, I'd say it might be possible to have big monsters in starring roles. They just wouldn't look like the overgrown dinosaurs, lizards, and apes that are usually shown in sci-fi movies. The largest known land creature was a dinosaur called Brachiosaurus. It weighed in at about 80 tons. Let's suppose it grew to 140 tons, almost twice its actual size. The Brachiosaurus might be able to stand, but its first step would be a killer. Its legs, unable to support that much weight, would break. Researchers estimate that the heaviest possible animal, able to walk on all fours, could weigh no more than 100 tons. This predatory reptile is called a Dimetrodon. He roamed the Earth about 280 million years ago, living in tropical swamps we now know as Texas and Oklahoma. Well, it's thought that during the course of evolution, the Dimetrodon may have as much as doubled in size. According to the rules of geometry, as he scaled up, his volume went up much faster than his surface area did. But a counterintuitive observation was made. The surface area of the sail on his back increased disproportionately. At Harvard's Museum of Comparative Zoology, Professor Hans Suess studies the Dimetrodon.
The nature of the sail in Dimetrodon has been the matter of a great deal of speculation. First, it was proposed that it was perhaps something to camouflage Dimetrodon in vegetation. Somebody in the late 19th century came up with the very original, if bizarre, notion that it helped it somehow to skid across ice as a navigational device. But more recently, particularly since about the mid-1940s, it has been repeatedly suggested that the sail served as a heat exchange device. Dimetrodon, being reptilian in its physiology, would have had the problem to adjust its body temperature to the environment constantly because it was unable to maintain a constant body temperature by itself. The vertebrae of Dimetrodon have very elongate neural spines, which are grooved both in front and back. And it's generally assumed that these grooves carried blood vessels going to the cell. Again, the blood vessels could carry this warm blood to the cell, radiate off excess heat, and then the cooled down blood could come back to the animal.
The heat an animal generates is proportional to its body volume, and radiating heat is a function of surface area. So one would predict that if the sail were involved in heat exchange, its surface area would increase proportionately to body volume. As we've seen, body volume scales up with the cube of the scaling factor, while surface area scales with the square. If the heat exchange theory were true, and therefore sail surface area had to keep up with body volume, we'd expect area to scale even more, to the 1.5 power. In fact, the actual observation was 1.6.
So this is as close an approximation as we can possibly get in nature in such a case. And it's very powerful evidence that indeed the sail was used as a temperature regulating device.
For most things in nature, a change in size is also accompanied by a change in proportion of parts to the whole. Just think about the way people grow. An adult is not simply a scaled-up baby. A baby's head relative to the size of its body is much bigger than that of an adult. Even the proportions of the facial features are different.
Green one?
A baby's nose is about 2/3 down the distance from the top of its head to its chin. But in the adult, the nose is about 1/2 of the way down. And the arms of a baby are shorter relative to the size of its body than are arms of a full-grown person.
Yeah.
Understanding how the proportions of our features change as we grow and predicting those changes could have valuable social consequences. Say a 3-year-old child is kidnapped. 2 years later, her parents and the FBI are still looking for her. But what does she look like?
The first 48 hours that a child is missing is the most crucial time. And then after that, as the years go by, those photographs become a real liability. As opposed to an asset, because the child just doesn't look like that at all anymore. So what we're trying to do is provide a credible likeness, a credible possibility of what that child might look like.
Conceptual artist Nancy Berson and computer scientist David Kramlich, co-founders of Face Systems Incorporated in New York, have devised a computer technique that simulates aging.
The idea is that the child will age in a way that is similar to his siblings or parents, and that the changes in the shape of the face will not be identical to, but will be similar to. So we try and create a composite face between that of the child and the sibling or the parent. So it's sort of an in-between face, if you will. What we're going to see here is a sequence of pictures wherein we age a photo of a child to his current age. The child that we see here is been kidnapped. The photo here is of him at 6 months. He's currently 5 years old. He is Chris Fulmer. This is his father, Scott, at age 10 years. And what we've done in this picture is just to combine the two in a very rough composite aligned on the eyes. This is a first of the refined composites that we did, where we warped the image of the child, Chris, to a shape similar to that of his father's head, and then combined the two images. When we warp the picture, what we're doing is decomposing the picture into a collection of polygons and then manipulating or changing the shapes of those individual polygons to effect a change in the whole image. And we did another version of that that is slightly older, and this we estimate is the child as he would appear now at age 5. Currently, the compositing technique relies on the fact that the child who's been kidnapped has siblings or parents who can be identified. It doesn't work for adopted children. So we'd like to expand the technique to work with photos of adopted children based solely on growth parameters so that we can modify a photo of a child without compositing it.
Aging a child's picture in such a way as to project what he or she might look like today is a delicate process. It combines artistic intuition and detailed observations made of children in many stages of growth. We've seen geometry manifested in nature in many ways, dealing with the problem of growth and dealing with matters of scale, the relationship of volume to surface area. But there's another expression of geometry in nature: patterns. The essence of pattern, natural or man-made, is repetition. These patterns have one feature in common. They use repeated shapes to cover a plane surface without leaving gaps. If we think of the shapes as tiles, we can call the pattern a tiling. This set of tiles consists of squares, and as you can see, when I line them up edge to edge, they form a tiling. Something I should make clear right away is the tiling actually refers to a plane. I'm not going to bother extending my square tiles, but you can see that the pattern I've created could be repeated in all directions to cover larger and larger portions of the plane. These tiles are equilateral triangles, and with no trouble at all, I can tile the plane with them. How about these pentagons? No luck. No matter how I crunch them together, there are still gaps in between. The simple shapes I'm using are called regular polygons. A geometric figure is a regular polygon if it has sides of equal length and equal interior angles. The sides of a square are equal, and each of the 4 interior angles equal 90 degrees. The same is true of our equilateral triangles, except that the interior angles are each 60 degrees. In fact, this formula determines the size and degrees of an interior angle of any regular polygon. To check this for triangles, make n equal to 3. Now, regular pentagons also have equal sides and interior angles, but they didn't work to tile a plane. We can discover what other regular polygons will work by mixing a little algebra with our geometry. If we look again at a tiling of triangles, we can make some observations that will help. Choose any point in the pattern where the endpoints of edges meet. We call any such point a vertex. For every vertex of this tiling, you see that there are 6 triangles that meet there. We can also see that the sum of the angles around each vertex equals 360 degrees. That's essential in a tiling of regular polygons. If the angles add up to less than 360 degrees, there'll be gaps and we won't have a tiling. If they add up to more than 360 degrees, the polygons will have to overlap, so that wouldn't be a tiling either. In general, we can call a polygon that has n sides an n-gon. Using this terminology, a triangle is a 3-gon, a square is a 4-gon, and so on. To explore possible tilings, we specify which n-gon we're using, and we want to know how many of these n-gons we'll find at each vertex. Call that number m. We know the formula for the interior angle of an n-gon, so now we can say that m of these interior angles equals 360 degrees. Where does this equation get us? Well, let's isolate m on one side of the equation, and let's say n is 3. Solving for m, we get 6. Now, a 3-gon is a triangle, so this checks. We already found that we need 6 triangles meeting at one vertex to tile the plane. If n is 4, m is 4, which corresponds to our pattern of squares. If n is 5, however, m is 10/3, so there is no whole number solution for the 5-gon, confirming our experiment with pentagons. If n is 6, m is 3. This tells us that 6-gons, or hexagons, should tile a plane. And here's the very pattern. As you can see, we do in fact have 3 hexagons meeting at each vertex. If n is 7, m is 14/5. Again, no integer solution is possible. What about octagons? N is 8, and m is 16/6. No go. In fact, there aren't any more integer solutions. And we can see why from the equation. We're dividing 2n by just a bit less than n, so no matter how large n becomes, m will always stay between 2 and 3. So it turns out that only 3 regular polygons, the equilateral triangle, the square, and the hexagon, will tile a plane. It's natural to ask whether there are combinations of regular polygons that fill the bill. That sounds considerably harder, but in fact, we can use all three of these shapes in one tiling, like this. Our conditions for tiling are indeed fulfilled. There are no gaps or overlaps, and the pattern is the same at every vertex. No matter which vertex you examine, there are two squares, a hexagon, and a triangle that meet there. All the patterns we've seen here fall into the same category. They're all called periodic tilings. Here's all that means. If I outline a portion of this tiling on a transparency, it's possible to slide the transparency along without rotating it until the outline exactly matches another section of the tiling. There are an infinite number of periodic tilings, but there are also an infinite number of non-periodic tilings. Here's an example of a non-periodic tiling made up of isosceles triangles. No section of this tiling slides directly over another section. We're using isosceles triangles because you can't make non-periodic tilings out of regular polygons, like the equilateral triangles we saw earlier. As far as we know, every shape you can use to construct a non-periodic tiling can also be used to form a periodic one. If we rearrange our isosceles triangles and slide and match the outline of a triangle, you can see that this tiling is periodic. For a long time, mathematicians believed that this would also be true for any set of shapes that tile. But in 1964, the first set of tiles was found that permits only non-periodic tiling. No wonder it took so long to find. The set contains 20,000 different shapes. Over the next several years, that figure fell to under 100. But it was still amazing when Roger Penrose, a mathematical physicist at Oxford, found a new set that would do the job with just 2 tiles. And here they are. These patterns are examples of non-periodic tiling made up of just these 2 shapes, what Penrose calls darts and kites. Here's one of the many tilings that can be made from Penrose tiles. We can discern a pattern of decagons, but this tiling is not periodic because we can't perform a simple slide and match the outline of a decagon exactly. But if we allow rotation, we can discover another kind of order in the pattern. Let's rotate these shapes 36 degrees, or 1/10 of a turn. The pattern looks the same as it did originally. The same is true for every subsequent 1/10 of a turn. This kind of order is called tenfold symmetry. If we make 1/5 turns, or rotations of 72 degrees, we can see that this tiling also exhibits 5-fold symmetry. In the mid-1970s, Penrose's discovery was a big hit in recreational mathematics circles, but his work was no more than a passing interest to physicists at the National Bureau of Standards, who in 1982 were looking for new ultra-strong alloys of aluminum. Now, manganese doesn't ordinarily alloy with aluminum, but the experimenters produced small crystals by cooling mixtures of the 2 metals at the rate of millions of degrees per second. Following routine procedures, chemist Daniel Shechtman began a series of tests to determine the atomic structure of the new crystals. But there was nothing routine about what Shechtman found. The atomic pictures he discovered were so startling that it took Shechtman 3 years to convince his colleagues they were real. Why did Shechtman encounter such resistance? Because his picture and the crystal that produced it defied one of the absolutely classical rules of crystallography. These laws were established early in the 19th century when all the known crystal patterns were cataloged. One rule summarized the symmetries possible in a crystal. This is a model of a crystal lattice. Imagine a line connecting these 2 atoms. Now, when I rotate the crystal a 1/4 turn, all the atoms line up. I'll go back to my original position so you can check. With each successive 1/4 turn, the same alignment occurs. And after 4 turns, I come back to my original position. This crystal is said to exhibit 1/4 turn or 4-fold symmetry. Now, according to the traditional rule, rotating a crystal could produce these identical patterns of atoms with every 1/2 turn, third of a turn, quarter turn as we've seen, or sixth of a turn. But repetitions occurring at fifths and tenths of a turn were not found. Yet this is exactly what Shechtman discovered in the new aluminum crystal. Here's the actual diffraction pattern Shechtman observed in the aluminum alloy. Although the alloy clearly has a crystal-like structure, it violates the most elementary principle of crystallography. The diffraction pattern is not periodic. In their efforts to understand the surprising picture, physicists spotted a revealing connection. This non-periodic pattern with tenfold rotational symmetry is a physical replica of a Penrose tiling. So once again, pure mathematical research anticipates scientific applications. Penrose's discovery of non-periodic tilings with fivefold symmetry is helping to fuel a major re-examination of our theory of crystals. Mathematics is fundamental to our understanding of scale, growth, and patterns, but in an even more important way, it's an essential tool for explaining what we don't understand.